There's a tantalizing similarity between rotations in ordinary space, which take us from one coordinate grid to another, and the kind of strange-looking rotation that occurs in a space-time diagram when you go from one frame of reference to another, where the axes kind of come together. So the question is there a way in which the Lorentz transformation, taking us from one space-time reference frame to another space-time reference frame, can be described in a language that's similar to the language of rotations in ordinary space? And the answer to that question is yes. It makes use of hyperbolic cosines and sines instead of the ordinary cosines and sines. And I'd like to just take you through that, as it gives us another way of writing mathematically the Lorentz transformation. I'm going to break this little calculation up into 3 or 4 little pieces, so let's just go through them one by one. I'm going to begin with what might look like a kind of strange definition of a variable that will play the role of an angle. But the definition is going to be e to the phi. This now defines the variable phi is equal to the square root of 1 plus v over c divided by 1 minus v over c, where v is, again, the relative velocity of 2 different frames of reference. And therefore, e to the minus phi is that guy flipped upside down, 1 minus v over c divided by 1 plus v over c. And I want to play around with this definition to put it in a particularly suggestive form. So point number 1 that I'm going to make, with that definition of phi, you can show that gamma is equal to e to the phi plus e to the minus phi over 2. How do you do that? Well, just straightforward calculation. Let's spell it out. So e to the phi, square root of 1 plus v over c, 1 minus v over c, plus e to the minus phi, square root of 1 minus v over c, 1 plus v over c. And we're going to take 1/2 of this. All right? In order to evaluate that, let's put it all over a common denominator. Let's put it all over 1 minus v over c times 1 plus v over c downstairs. And what will we have upstairs? Well, we'll have 2 terms. So from this guy over here, we will have multiplied this guy by 1 plus v over c. So that will give us the square root of, if you will, 1 plus v over c squared from the first term over here. From the second term over here, I'll have something of exactly the same sort. So if I can squeeze that in over here, plus the square root of 1 minus v over c squared divided by the product here, which I'll simplify and write that in the form 1 minus v squared over c squared. That is the same. All right, so putting those 2 guys together, the square roots take away the squares on top, so we get 1 plus v over c plus 1 minus v over c from the second term, and both of these guys are over the square root of 1 minus v squared over c squared. And we see that the v over c goes against the v over c. We get 2 here, but bear in mind there's a factor of 1/2 that I should have carried over, but there it is. So with that half, that factor of 2 turns into 1, and we are left with 1 over the square root of 1 minus v squared over c squared, which of course is our friend gamma. So indeed, we've now established part 1 of this little calculation, that gamma can be written in this way, e to the phi plus e to the minus phi over 2. Now, why is that useful? Not that useful yet, but let's just keep on going. And let's look at point number 2 over here. And point number 2 is the claim that sinh of phi, the hyperbolic sign of this variable phi, can be written as v over c times gamma. Okay? So what is sinh phi? Well, of course, sinh phi, maybe it's worth saying over here, since I'm going to make use of it, that this guy over here is the same thing as cosh phi. So this can also be written as gamma equals cosh phi, where by definition, cosh phi is that particular combination of the exponentials. Good. So the claim is that sinh phi, which is the combination where you have a minus sign instead of a plus sign, can be written in terms of v as v over c times gamma. How do you show that? Well, remember that cosh squared phi minus sinh squared phi, this plays the same role for hyperbolic cosines and sines as the sum of the squares does for the ordinary ones. This is always equal to 1. And now we're in good shape because writing sinh squared phi is equal to cosh squared of phi minus 1. We now can make use of what we derived over here, that cosh phi is nothing but gamma. So we can plug that in this expression here and write this as gamma squared minus 1. Gamma squared, of course, is 1 over 1 minus v over c squared. If we want to subtract off 1, we can do that by subtracting off 1 minus v over c squared over 1 minus v over c squared. And as you see, the 1 will cancel against the 1. The minus sign will turn that into a plus sign. And we will be left with v over c squared times 1 over 1 minus v over c squared. So this is sinh squared of phi. If we take the square root of that to get sinh of phi, we'll have sinh of phi, therefore, is equal to v over c from the guy in front times 1 over the square root of 1 minus v over c squared, which is indeed v over c times gamma, as we advertised. Again, it should not at all be obvious to you why these manipulations matter, but they will in just a moment. Okay, so that's part 2 of the calculation. Now for part 3. So for part 3, I'm just going to put these two together, and we remember what they are, so we can clear this away and give ourselves a little bit of room. We have found that gamma is equal to cosh phi, and we have found that sinh phi, for this definition of phi, is equal to v over c times gamma. And the reason now why we care about this, putting it together, is that when we look at the Lorentz transformation, of course, involves gamma and v over c times gamma. So let's now rewrite the Lorentz transformation in these variables. So for instance, we know that t prime is equal to gamma times t minus vx over c squared, which we can now write as, well, for the gamma we have cosh phi. So we have cosh phi times t from this first term. Here we have a gamma times v over c with an additional factor of c that we will need to include. So that combination gives us sinh phi times x over c. And here we have a transformation that starts to look like a rotation, albeit an exotic rotation since we're using hyperbolic angles, but nevertheless, this looks very similar to the transformation from xy to x prime y prime. Okay, that's half of the story. What about the other half? X prime is equal to gamma times x minus vt. Well, we can plug in for gamma cosh phi here as well. So we get a cosh phi times x over here. What's the next term? Well, we have a gamma v. We know that gamma v equals c sinh phi. So let's write this guy as the second term just for the heck of it, v over c gamma times ct. Just put a c up and down. And putting it that way, we see that we can just put in our sinh in the second term. So then we can write this as cosh phi times x minus sinh phi times ct. And there we have it, writing our Lorentz transformation in terms of coshes and sinh. Let me also note that if you look at tanh phi, that, of course, is sinh phi divided by cosh phi. And plugging in from what we have above, we have v over c times gamma divided by gamma. So that is simply equal to v over c. So the way that you can think about this is as follows. So if you give me the speed of one frame relative to another, I can use that to find an angle phi by solving this equation. And then I can take that angle and plug it into a transformation from t and x to t prime and x prime, where the transformation over here looks very much like a rotation with some different signs. And replace, when I say signs there, I mean S-I-G-N, different signs, because normally when you do the rotations in 2 dimensions, you have one minus sign and one plus sign. Here we've got 2 minus signs. That reflects the fact that we're doing space and time as opposed to space and space. But there you have a nice way of representing the Lorentz transformation that looks very much like a rotation in this exotic space. So if I write this down in terms of ct prime and x prime, I can make it look even a little bit nicer. And if I put this in matrix form, now it really does start to look like a rotation. If you closed your eyes and you didn't see the h in sinh and cosh, it would look like a rotation. It's not in the Euclidean sense. It is a rotation in this hyperbolic sense. So just to compare that, here is what we would have for space-to-space transformation. And now we have space-to-time in a form that looks very similar. So it's a nice way of thinking about how the Lorentz transformation can be given a kind of geometrical interpretation in terms of this exotic rotation.